Hi everyone, we are Presentation Group 4, and today we will be talking about the Group 16 elements, also known as the chalcogens. The figure below outlines the periodic table trends for the Group 16 elements, which consist of oxygen, sulfur, selenium, tellurium, and polonium. As we can see, the observed elemental properties almost entirely agree with the expected periodic trends. The ionization energy and electron affinity of each element increases moving up the group, while the atomic radius and metallic behavior of each element increases moving down the group. The only exception to these trends is the electron affinity of oxygen, which is the smallest of the chalcogens. This is a result of oxygen's small atomic radius, which increases the electron density of its 2p valence shell. Thus, any incoming electrons experience higher repulsive electromagnetic forces than with any other group 16 element. Generally speaking, all chalcogens have appreciable reactivity on account of their unfilled valence shells, which take on an S2p4 configuration. The reactivity of the chalcogens typically increases as their atomic radii decrease, meaning that reactivity of each element increases moving up the group, with oxygen being the most reactive. Each element's tendency towards reduction or oxidation varies within the group. Oxygen almost always gains electrons as a result of its high electronegativity, taking on an oxidation state of -2. Sulfur, selenium, and tellurium are capable of both gaining and donating electrons, and thus often take on oxidation states which range from -2 to +6. Polonium, on account of its large size and high number of electrons, tends to only lose electrons, with the most common oxidation states being +2 and +4. Oxygen's high reactivity is reflected by its ability to form a variety of covalent and ionic bonds, as well as its tendency to form double and triple bonds. Sulfur is additionally able to form several types of covalent and ionic bonds, as well as double bonds. Selenium and tellurium are capable of occasionally forming double bonds, but these instances are rare. Polonium, in contrast to the other chalcogens, usually only forms ionic bonds. Sulfur additionally has a high catenation tendency, meaning that it can relatively easily form covalent bonds with itself. This trend in catenation decreases from selenium to polonium as the element's atomic radii increase and their effective charges decrease, as the increasing radius and shielding effects weaken the strength of the covalent bond. Sulfur's high catenation tendency also means that it is able to form several different crystalline structures, or allotropes. Like the trend in catenation, the tendency of the chalcogens to form different allotropes decreases moving from selenium to polonium. Finally, the metallic behavior of each chalcogen varies within the group. Oxygen, sulfur, and selenium are considered to be nonmetals, while tellurium is a metalloid and polonium is a metal.
Oxygen exists in two allotropes, O2, which is paramagnetic, and O3, which is diamagnetic. Some important chemical reactions involving oxygen are combustion, oxidation, and metabolism. O3 absorbs UV radiation below 320 nanometers and is photolytically decomposed to O2. This ozone decomposition occurs in the atmosphere and happens naturally, but can be accelerated by pollution. Conversely, O2 can produce two oxygen atoms under UV radiation, and then react with oxygen gas to form ozone, as seen in the reaction below. Oxygen also reacts with metals to form metal oxides that are mainly ionic in nature, and are often used in nanomaterials. Oxygen can also dissolve in water to form hydroxides, important in many chemicals and chemical reactions. Oxygen-containing compounds range from organic to inorganic, including peroxides, alcohols, ketones, aldehydes, anhydrides, etc., all of which are important in life-sustaining biochemical reactions. Sulfur contains the most allotropes known than any other element. S, S2, S4, S6, and S8 exist as gases, with the orthorhombic form being the most stable at room temperature. Sulfur reacts with oxygen to form the common sulfur oxides SO2 and SO3, used in the manufacture of sulfuric acid shown below. Sulfuric acid has high affinity for water and acts as a dehydrate agent, used in the production of phosphate fertilizers, explosives, automobile batteries, etc. Many sulfur and oxygen-containing compounds and ions are important acids or conjugate bases. For example, thiosulfate is used as a moderate reducing agent in the analytical determination of iodine. Selenium is a poisonous element, but trace amounts of the element are essential for life. Selenium is often used as a semiconductor and is photoconductive, meaning that the electrical conductivity increases in the presence of light. Sc reacts with water to form hydrogen selenide, a colorless and flammable gas. Fe burns in air as a blue flame and forms solid selenium dioxide. It also reacts with metals to form selenides, such as zinc selenide used in infrared optics. Tellurium is a metalloid that also displays photoconductivity. Te reacts with halogens to form halides and combines with most metals at high temperatures to form tellurides. Polonium is a very rare and radioactive element. All 33 isotopes are radioactive. PO dissolves easily in dilute acids, and the radioactive element is used as an alloy with beryllium to act as a neutron source for nuclear weapons. In relation to other elements, oxygen and sulfur are both abundant elements with a wide variety of important chemical and biological applications. They form many important organic and inorganic compounds necessary for life, such as water, thiols, alcohols, and carboxylic acids. Pollutants such as nitrogen oxides and chlorine from COCs can catalyze ozone decomposition, which is important when we consider climate change and green chemistry. Selenium and tellurium are used in semiconductors and photoconductive electronics, such as photocells and solar panels, and are also being developed into nanoproducts with biomedical applications. The figure on the right shows selenium and tellurium nanoparticles being used to carry plant and microbial extracts to be used as potential anti-cancer drugs and other biomedicine. Finally, tellurium is often used in metallurgy with copper, lead, and other metals to form useful objects such as automobiles, aircraft, utensils, and more.
Finally, here are some fun facts about the chalcogens. Lithium-sulfur batteries are popular in energy research due to sulfur cathodes' high theoretical capacities and the element's affordability due to its relative abundance in nature. Sulfur, selenium, and tellurium have additionally proven to be effective catalysts in hydrogen gas production via electrochemical water splitting, which might be important for energy production in the future. And lastly, polonium can be used as a static eliminator in paper rolling and synthetic fiber spinning, as the alpha particles that it emits neutralize negative charges. Here are our citations, and thank you for listening.